In this lecture we will learn about self-assembly. It is nothing but organization of structures to form a higher level structure. So, how do we do that? We will see upon in this particular lecture. So, we can see self-assembly is nothing but spontaneous and reversible organization of molecular units into some ordered structure. So, there is some order which basically is incurred by this particular entities, molecular entities, which is very spontaneous in nature, and it is also reversible as well. And since it is spontaneous and reversible, it also acts on a very localized level. So, in this case we are building nanostructure and it starts constructing itself or it builds itself. So, we see molecular units, they go on to forming certain organizations, and it is self similar and it starts constructing itself. At the same time, there is a key role of weak interactions. So, weak interactions such as van der Waals forces, capillary action, capillary forces, or pi-pi bonds or the hydrogen bonds, they tend to also provide secondary stability to the particular unit or to particular organization to get higher level of order, and it eventually goes on to forming such as molecular crystals, self-assembled monolayers, thiols, and many other. So, we can see self-assembly is nothing but spontaneous and reversible organization of structures, molecular units, to form little bigger structures, and these are self-sustaining, and it means that it is constructing itself as the process goes on, and there is very much key role of weak forces such as van der Waals, hydrogen bonds, capillary forces, because they also tend to provide certain stability to the nanostructure, and it eventually goes on to forming more ordered structure such as molecular crystals, self-assembled monolayers, and so on. So, seeing that self-assembled monolayers, first of all they have highly ordered structure. So, their nature is highly ordered and it provides very tight packing and it forms very rapidly on the surface, but to attain a particular order, that is a time consuming step, or that is a the rate deciding step. It may require up to 15 hours to achieve a well ordered and a defect free self assembled monolayer. Its applications involve chemical sensing, wettability, controlling friction, corrosion protection, even patterning, or even semiconductor passivation. So, we can see that in self assembled monolayer we have a substrate, and that substrate is covered with certain head groups, and which is a tail region, and they go on to form becoming much more ordered, and they might have certain functional group on the top of their chain to render a certain functionality to the. So, we can see that this is nothing but some sort of a functional group. So, we have a substrate, over that we tend to deposit certain head groups that will attach itself to the substrate. Then it has a tail region, and then that tail is covered with certain functional group to impart certain functionality. So, we can see that they are much more ordered in nature, that they are very nicely ordered, and they are tightly packed. Also they can form very rapidly on the surface, but to organize them into very ordered structure, it requires much time, because they have to come and then basically conform to the forces which are acting around it to render a very ordered and a defect free self assembled monolayer. You can see that for switch or logic devices we need many functional units on the surface. Currently we have around 10 to the power 8 units which are there on a per centimeter square area, and depending on this conformation it can go as dense as 10 to the power 13 units per centimeter square. So, we have a possibility of increasing this number of this density of this functional chains by order of 10 to the power 5. So, that is the logic we are talking about. We can enhance it by 10 to the power 5 times or 1 lakh times to render a certain density to this material and impart much more functionality to even logic devices or switch devices. Their application also include chemical sensing, because if we have more number of such patterned surfaces on a particular substrate, then we can sense a particular gas or a media or any chemical functionality to a very high level. So, we can even when there is a very small ppm of a particular gas or chemical, we can sense it. Also utilized for either increasing the wettability or reducing the wettability, for controlling the friction, if we can impart certain layers which are much more resistant, which can provide us lubrication or non-adhering property. We can also provide corrosion protection to a surface. We can have certain patterned structures. So, if we have certain functionality and that functional groups will come, the head groups will come and adhere to a certain region, and then we can achieve functionality through those functional groups by this particular monolayers, and also it can be utilized for passivating the semiconducting surfaces. So, again there can be two approaches, first of all bottom approach or the top down approach, but the overall idea in the bottom approach is we control something at a molecular level, and then say if we have certain molecular level, then we can impart certain microstructural pattern to it, and then that microstructural pattern can again have certain nanostructured pattern. So, we have nano pattern over a micro pattern. So, we have substrate, then we have microstructural pattern over it, and this is a nano pattern. So, if we are starting from a nano pattern, then we go on to constructing a micro pattern, and then we deposit this micro pattern on a substrate, then we can basically here we are going from a bottom approach. It means we are combining couple of functional units, molecular units, go into forming certain nanostructures. Nanostructures go into forming a little higher level of micro pattern, and then that eventually is getting deposited on a substrate. Now, this is very useful in imparting certain functionality to a material. So, if we have this sort of scalability or length scale associated with that, we basically are going from nanostructure, from molecular structure to nanostructure to microstructure to impart certain functionality. That is nothing but bottom up approach. And how can we utilize them? We can play either with the surface tension or with the surface free energy. So, in this case, if we play with the functional group, we can provide either complete wetting. So, we can provide much more wetting to the surface, or we can also provide non-wetting to the surface. So, if we can control the functional groups to be coming out to be as say OH minus, then it has very high affinity for water. So, now we make the surface hydrophilic in nature. But in another case, if you take a methyl group, then methyl group will try to repel it, and because of that it can reduce much more non-wetting or hydrophobicity. So, we can see that methyl can have a hydrophobic nature, and that this alcohol OH minus can have much more hydrophilicity. So, we can somehow if we are playing with the surface tension or surface energy, we can impart a very different functionality of the surface. So, bulk is same, but only because of this functional unit. If it is alcohol group, it will have much more hydrophilicity. If it is a methyl group, it can have much more hydrophobicity. So, by playing with the surface energy or the surface tension, we can somehow impart very different or contrasting characteristic to a substrate. The substrate is the same, but only because of its surface we can control the overall functionality of this particular surface or substrate. So, we can again go by either top down approach or a bottom approach. So, in top down we take a bulk and we start fracturing it until we reach nano. So, in this case we are trying to break up the material. We break the material to achieve a finally nanostructure which are approximately couple of nanometers in dimension. On the other hand, if we go from molecular units, if we have molecular units, they go into forming certain nanostructures, and this can be achieved by imparting self assembly. So, now we can get from molecular units, we can get microstructure in one unit, but in this case we are breaking the material. So, there is much more wastage of material, but in this case we achieve everything in single step because of the self assembly. So, in the process what we are doing, we are saving the material as well. So, in this case again we are able to reach a couple of nanometer, but we are starting from molecular units which are sub nanometer in nature, and then because of self assembly we can get a structure which are couple of nanometer. So, what we are doing, the final product is the same, that we are achieving certain nanostructures, but one is, this is a top down approach and this is a bottom up approach. So, we can see in top down approach we take a bulk material which is very big, big in size. It can be couple of meters to that level, and basically we are just breaking the structure, and in the process we finally get which is a nano entity. But in bottom approach we go from molecular units, we will allow it to self assemble, and then we get a final nanostructure, and that is again nanometer in size. This is a single step. So, we basically end up saving the material, because we are starting from a entity which is much more smaller than a nanometer, and this gives us the advantage that we can also somehow control the overall assemblage of this particular system from molecular units to a bigger structure. So, we can see first of all we have a head group which is lying on a substrate. So, we have a substrate, then we have a head group with certain tail, and then a functional group. So, we have head and this is a tail, or it is also called as spacer. So, depending on the length of this tail, we can somehow control how this structure will come out to be. So, in one case we can make the surface highly wetting or non-wetting. So, we can make either wet or non-wetting surfaces just by controlling if it is alcohol or if it is methyl. So, if we can somehow control this particular part, we can control the nature of wetting or non-wetting. At the same time, what we can do, we can also play with the chemical functionality. So, in this case we can make it physically either attractor to water or repellent to water. We can also make it sure, we can also utilize a certain chemical, we can also utilize chemical functionality to impart certain characteristic to a material. So, we can somehow impart some chemical affinity only to a specified region and not to the remaining region. That might be required in certain cases, because in case we want a dual functionality, in one case we might require its attraction with something, in another case we might its repulsion. So, we can from chemical functionality we can achieve duality or dual functionality from this particular arrangement. So, we can see that we can achieve this chemical functionality. So, we can get either a deposition, say this particular layer is good for deposition of one entity and not for the second entity. So, we can apply some sort of a resist, so which will not allow any entity to grow onto it, but whereas other portion will allow the growth of the secondary unit, and this might be required for constructing say certain chips or certain electronic circuits. So, in that part this functionality will be very useful. So, in certain cases we want to build up structures which go in height. So, we might require deposition along certain areas and not along other areas, and later on we can go upon making something else over it and then somehow joining them series or parallel, or it can be any particular structure. So, this chemical functionality is very good, because that will allow us to selectively deposit required materials. So, that is the advantage of controlling the chemical functionality or even controlling the wetting. So, it can allow us to achieve very low friction or to resist the deposition of water or any humidity on those surfaces of the electronic components when humidity is very high in the atmosphere. So, that is the advantage of this particular thing. And depending on the spacer, we can also somehow control the overall nature of this self assembly. So, if we have this tail group, say tail group is like this, and then we have a functional unit which is basically trying to form the network. So, we have something called spacer, and then this is nothing but some sort of a joining or networker. So, assembly of this one will lead to, so we can achieve certain structures. So, we can achieve certain structures if we the way we wanted to, or we can also get some other sort of structures depending on our networker. if it requires a 6-fold, 4-fold, and so on. So we can get many different type of variety of these structures. So the spacer width and height, it will be very critical. So that will decide what is the overall region which is available for us for deposition. So in one case we can have some sort of a resist, this one can be a resist. So now we have certain region which is available for deposition, and in this case we can control the deposits. So once we are depositing something, we can achieve which is called deposit, which is getting deposited onto this particular available region. And now this functionality, so we have some sort of a resist, and now we are getting deposit, and this is now forming a structure within this particular pore. So we are seeing that somehow we are able to this is nothing but a network formation. So we are forming some sort of a network. So depending on that, we can achieve very nice arrangement of we can achieve very nice network out here, and it can be self consistent or self propagating. So we can, what we can get once we start another process, it can allow deposition only along this particular region, and because of its confined nature we can control the overall diameter of this one, and also the angularity can also be controlled depending on this our network functional group. So depending on that, it will provide the overall angle to it, and the length will be decided by the spacer or the tail group. So from that we can now achieve some sort of a network for which is required for the formation of nanostructure. Excuse me. Now depending on that, we can also control the pore size. If we control the overall the length of our spacer or the tail group, we can also control how thin or what will be the overall radius of that particular pore which can form. So if you have a little longer spacer, we might get something like this, but if we restrict our spacer, we can also get pores which are much more smaller. So in this case we get very bigger pore in this case, and then we can also get a smaller pore when we have a, so we can keep our networker the same, but in this case our the length of our spacer is this much, but in this case our spacer length is only this much. So accordingly we can somehow control how much is the spacer length, and then what is the structure we get. So in one case we can get structure which is more like this, in another case we will get something like this. At the same time, if we somehow can control the overall geometry of our spacer, then again we can control the pore structure. So if we want to provide much more surface area to the pore, we might require the pore to be very tortuous. So in that case we might require a different geometry of our spacer. So our spacer can be more like this. So we can have a spacer which can be more like this. So in that case what we will get? In that case we will get more like this. Now we can see, now we have pore which is much more flowery kind. So that is the part we can see. So just by changing the geometry of our spacer, we can somehow control. So in this case if we had a hexagonal pore and very symmetric pore, in this case we get more of a flowery type pore which can be obtained. And again the thickness of the pore, the diameter of this pore can be altered depending on the spacer geometry. So we can see the networker is the same in this case. We can again change the networker. If we can make it square or something like that, we can also attain structures which are like this. So depending on our networker, we can also change the porosity type and size. So that is the overall combination of our spacer, how the spacer has to be, what is the geometry of the spacer, and what is the how the networker will fit into the picture to give a resultant pore. And to achieve a certain functionality, or in order to achieve that we enhance the surface, the surface area of the pore, in order to trap certain signals for it, or to allow a growth of certain entity into it, or to provide certain geometry or construction to the newly deposited structure into the pore. The control of pore size is very essential, and that can be controlled by playing around with the networker or the spacer. So that is the one which makes this assembly much more useful to us. Again, we can see in lotus effect is also controlled by the nanostructure. So we can see it can impart very high non-wetting. So wetability is one of the concerns, and that is governed by the microstructure. So we can see if you have a lotus leaf, if you have a lotus leaf and you drop a droplet of water, if it sits onto it, it basically doesn't wet. So we have the surface of the lotus leaf, and then we have contact angles which are exceeding which are exceeding around 160-165 degrees. So that makes the surface super hydrophobic. So in this case we have a structure, we have the overall lotus leaf surface and it has certain protrusions on the surface. If you see the cross section of it, you will find there are certain micro protrusions which are sitting here and there. So these are nothing but micro protrusions. Generally the lotus leaf, the non-wetting on lotus leaf is thought to be governed by the chemical composition or the epicuticular wax which is present on the lotus leaf surface. But it is apart from the non-wetting nature of this epicuticular wax, if had there been no roughness, so the minimum surface energy of the surface will lead to a maximum contact angle of 120 degrees. So maximum contact angle of only 120 degrees can be obtained if the surface has the least surface energy. But in lotus leaf we are seeing contact angles in excess of 160 degrees. So it means that chemistry of a surface is not enough on its own to govern the non-wetting. So there has to be some extra feature which is governing the overall non-wetting to increase the contact angle from 120 to 160 degrees. So these micro protrusions are the first regions which basically enhance the wetting angle and again contact angle, and then again there are certain nano hairs which are present on the each of protrusion. So each of protrusion will have certain nano hair which is present on the surface. So that in turn also increases the roughness by order of couple of times, and this roughness is the one which either increases the wetting or non-wetting depending on the inherent nature of the surface. So if surface itself is non-wetting, the degree of non-wetting increases because of the micro roughness and then because of a nano roughness, and vice versa as well. If the surface itself is hydrophilic in nature, it is water attracting, the contact angle will go down drastically by adding roughness to it. So roughness will either enhance wetting when inherent surface itself is it has a wetting characteristic, or it will also increase non-wetting if the inherent surface is non-wetting in nature. So because of that we have the apparent contact angle is now increased because our initial surface is epicuticular wax, it is hydrophilic in nature. So macro protrusion enhance this contact angle to a high degree, so it can go up to even up to like 140 degrees, and from there 120 to maybe 130 to 140 degrees, and then apparently the nano roughness enhances it further down to 160 degrees or higher than that. So that is the overall role of nanostructure which are present on the surface of lotus to impart non-wetting to lotus leaf. And there is then certain classes of self-assignment monolayers. First we have Langmuir-Bloggett films. These are formed basically by the weak or electrostatic forces or certain ionic forces, ionic bonding between the surface and the film. They have energy to the order of 50 kilojoules per mole. followed by thiols, or these are also called self-assembled monolayers, and they generally form covalent bonds and they have energy to the order of 150 to 200 kilojoules per mole. And then siliconization, which generally forms covalent bonds with silicon oxide or silicon carbide, and it has stability energy of around 300 to 450 kilojoules per mole. So, for Langmuir blockade, we need to have a surface on which we have a tail group, head group, and then a tail group which is basically adhering onto it. But again, this tail group should have concentration. This can be again a liquid, or it can be a substrate. Ideally, the concentration of this particular entity, the concentration of the film, or the concentration of the secondary chemical should be much less than that of a missile concentration. So, concentration should be much lesser than missile concentration. Otherwise, these all head groups will combine and they will form a missile. If concentration is very high, they will go on to forming a missile structure. So, this will form a missile when the concentration of this particular chemical is much higher than the missile concentration. So, the concentration of this particular entity or the Langmuir blockade film, to form a Langmuir blockade film, the concentration of the chemical has to be much lesser than a missile concentration, so that it can survive on the surface and get equally dispersed to form a very regular or a structured layer onto the substrate. Then again we have thiols. So, this is nothing but a sulfur bonding with the functional group or the hydrogen. It generally is a covalent bond with energy of 150 to 200 kilojoules per mole. And then third one we have siliconization or silicon, which is bonded with other 4 hydrogen atoms. So, hydrogen atoms can again be replaced by certain functional group later on. So, we can see examples of self-assembled monolayers. So, we have Langmuir blockade. It generally is very prominent on the alkyl acids such as RCOH. It is predominant on metal oxide, Al2O3 AgO, or polar or ionic surfaces. Whereas thiols or self-assembly, is dictated by thiols or phosphonates. It has a very high affinity for noble materials such as gold, silver, copper, and so on. Then third is the siliconization. So, siliconization is dominated by the silicon. So, it has either functional group or some hydrogen or halides which are available on the other side to complete its valency of 4. Utilized for the silica hydrated or other oxides, it can form on silica hydrated or other oxides. So, we can see the 3 self-assembled monolayers: Langmuir blockade, self-assembly, which is nothing but thiols, and then siliconization which can occur. For the Langmuir blockade assembly, first of all we need to have concentration which is much below that concentration of the missile. So, first thing is that we can first of all disperse this particular chemical. So, we have some sort of a barrier which will not allow the, so we have this head and tail group which are dispersed onto a liquid, and then we have some sort of a barrier or a Teflon barrier which will not allow these particles to come into it. So, once we start squeezing it through, then these particular entities, they will start coming closer and closer, and then they will form like this. So, we can see that there are certain molecules which are either amphiphilic or hydrophilic. So, one entity will go on to this particular fluid media. So, we have a film which is forming, and then we start compressing it, and the compression of this one will decide what is the distance between the chains. We can also do secondary treatment. We can also somehow compress it. Once we compress it, we can form very dense layers, and if you want to coat it on a certain entity, so we can somehow take it something like this. We can let these molecules come like this, or and then we can put our substrate out here, and then we start pulling it up. So, in the process, if we start lifting it up, then what we get is deposition of all these entities on the surface of this particular substrate. or we can also make it go like this to finally deposit it onto its surface. In the process we can deposit them. So, we can see that we can deposit either the hydrophilic end or the hydrophobic end to the substrate. This is nothing but substrate. So, now what we are getting? We are getting very ordered film. Ordered films which are basically getting deposited onto that, and these the overall the substrate can also the porosity on this particular films can also be controlled. So, we can see that porosity or the distance between chains can be controlled. Now, the control of porosity is very critical in this particular aspect, because that will decide what all chemicals or what all chemicals can permeate through this particular film. So, if you want to impart functionality that only hydrogen should be able to pass through, or only oxygen should be able to pass through, or only certain entities can pass through, we can control the overall porosity of this Langmuir blockade films. So, that can be dictated by compressing or by applying lower pressure, lower compaction, so that the all the chains are sparsely packed. So, in that case we can control the density of these particular amphiphilic or the hydrophilic entities, all these chains on a particular substrate. So, that gives us the control that we can utilize this Langmuir blockade assembly to somehow play with the nature and the density of this particular film, and impart particular permeability or porosity to all these films. And again, the stability of this particular chain is also dictated by the overall hydrogen, either the hydrogen bonds or the van der Waals forces. So, the weak forces also dictate the stability of films. So, the weak forces also dictate the stability of this film or the Langmuir blockade assembly to provide much more crystallinity or stability or ordered nature to the films. And the second part can again of self assembly, it can again be attained by these thiols. So, we can get functionalized alkane thiols on the gold surfaces. So, we can have a solution which is a thiol solution, and this sulfur group has high affinity for the noble materials such as gold, silver, copper and so on. And once we impart, if we can make certain structure, so we can electro deposit sputter deposit gold, a certain pattern of gold. So, we have silicon layer, and over that we can provide certain construction of gold assembly by either sputtering or any other technique, and then deposit this this structure into a thiol solution. So, what we can get finally is a certain structure of gold which is now thiol attached to it with certain functional group. So, now eventually what we are getting? We are getting a substrate which is nothing but our silicon, and then we have a very nicely layer structured of thiol layer. So, we can get a very good monolayer. So, we can get a self assembly of this particular structure or thiol on a gold on a silicon substrate, which is again certain deposition of gold on the substrate. So, we can attain the self assembly by allowing the particular pattern deposition of gold on a silicon surface, and then once we deposit that particular surface of silicon which is now gold in a certain pattern, that particular pattern zone of gold will now attract the thiol group, and thiol group with certain functionality to it, any carbonaceous chain to it, will now get attached to the gold particle to give a monolayer of that particular chain. So, in this particular case, now we are getting a self assembly of this sulfur on this particular chain. And in salinization, we are utilizing a particular functional group. So, we have a functional group of some R, and that is combined with either hydrogen or ethanol. So, we have to satisfy its valency. So, if it is particular entity N, this will be 4 minus that particular N, and then what we are attaining, silicon HX. So, what essentially what is happening, we have chain. So, we have a silicon group. So, if we have R here and say X here, and then we have OH, and then we have certain functional group. So, in this case we are removing this function out here. So, what we are getting finally is a combination of silicon, R, oxygen, and then R dash. So, essentially what we are getting a strong covalent bond. So, in this case that is what we are getting. So, we have a functional group of R, functional group of R dash, and then it combines with a third functional group of maybe say R double dash. So, in that case we are getting we can get a certain very strong covalent bond of silicon and with oxygen, and then that can result a very strong attachment of this particular silicon surface. But the problem with silicon is that now it has 4 arms. So, one arm has to go here, second arm here, third arm here, fourth arm here. So, we can get 4 order kind of entity out here. So, the overall problem here basically occurs that we can ideally we should get a structure which is more like this. So, we have substrate, and then we should get 3 combination of silicon with say one oxygen, oxygen, oxygen. The third one should have some R dash sort of a chain. So, we can get this sort of a structure, oxygen, 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 and then some sort of a R dash chain. But the problem that can happen is that instead of combining with one oxygen out here, it can break up that chain, and instead it can combine with R dash out here. So, it will lead to a chain which is in another direction and not in the top direction. So, we can see oxygen, oxygen, it can have R on this side, and then it can again have oxygen or R on this side. So, essentially we are getting a chain which is now not aligned to the other chains, but to some other to a different. So, we can have R dash, silicon, oxygen, R dash, but there are some certain other chains which are now going in different directions. So, this is not imparting a much density or alignment. So, the overall assemblage, the self assembly is now not distorting the arrangement. So, it is not a self assembly because it is not assembling on its own. So, that can be a problem associated with the silanes. So, we can see that they have very strong bonding with the oxygen because of it, because it is a covalent bond. So, it can give very strong alignment, very strong deposition of all this particular entity. So, we have oxygen, 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 and then we can have silicon which can combine with it, and then it can impart R dash or some other entity which it can provide a very nice layer, but it can also lead to a problem of distorting the overall geometry and then fracturing the overall concept of self assembly in this particular case. So, in comparison, we can see Langmuir-Bloggett films, they can be porous. So, we can also control the porosity depending on the structure kind of pressure or the kind of structure we use. Whereas thiols, they have very strong affinity for sulfur for noble materials. So, sulfur has a very high affinity for noble metals. So, we can deposit on a gold, copper or silver surfaces by sputter deposition, and then we can control where the thiol has to come. Whereas silanes, they tend to be highly explosive or toxic reducing agents. So, because they have a very high amount of hydrogen as well, and the bond is also very strong. So, in that particular process, once the bond breaks, it can release very high energy and make the thing explosive or toxic. The application of Langmuir blockade films applies in metal insulator semiconductors, biological membranes, or for drug delivery, chemistry of changing the chemistry of biologically active molecules, and even the modeling of the biological systems. Whereas thiols, they are easy to pattern via certain techniques such as lithography. They can be highly useful for the nano electromechanical systems, because it can also withstand very harsh chemical cleaning treatments. So, that is the advantage with the thiols, that you can utilize them in the micro electromechanical systems, and it can also reduce the overall wear or the harsh chemical environment that is that can predominate in such structures in the moving parts. Silane, they can adhere to glass fibers. So, again it can also be utilized for water repellent coatings. It can also initiate combustion in the compressed air stream. It can also be utilized for deposition of amorphous silicon on glass to stabilize the overall composite materials. So, there are certain applicability of this silane films as well, but they tend to be very explosive or toxic as well. So, that again it requires a better control, but these films they have very higher bond energy and they can be very stable as well. In certain pattern we can also somehow construct a selective hydrophobic and hydrophilic surfaces. So, if we select a particular entity and let us deposit gold onto that, and then if we can somehow control that we want to deposit only hydrophobic surfaces, and then we can coat it again, and then we can deposit a patterned surface again to deposit something else, maybe say hydrophilic surfaces only on other regions. So, we have phobic regions. So, we can have CH3 bond here, whereas we have OH bond. So, this is hydrophobic, whereas these surfaces are hydrophilic. So, in case when we want to impart a dual functionality to a material, we want certain regions to be hydrophobic and other regions to be hydrophilic, we can impart that particular functionality. So, we can have certain regions which are hydrophilic and hydrophobic. So, we can have certain regions. So, now this particular material can be tailored accordingly, that either we can want to capture hydrophobic or hydrophilicity. Hydrophobic nature might be required so that there is no contact of water on the surface, whereas hydrophilic can be required to impart certain lubrication layer so that they do not undergo corrosion to that extent or do not undergo wear to that extent. So, we might require hydrophobicity or hydrophilicity on the same platform. So, if a substrate requires both these functionalities, we can somehow tailor them and impart both of these features. So, if a particular material, say if a water droplet falls on this particular substrate, it will stick because it has a localized hydrophilic regions. At the same time, if a oil spills onto it, it will still try to stick it, because again you have certain amphiphilic regions which are available on the particular patterned surface. So, we can achieve dual functionality or duality in a particular surface, or if you want to control it vice versa, we can also eliminate that particular part by controlling the hydrophobicity or amphiphobicity on the patterned surface. Again, SAM can be self-assembled monolayers can be produced either by physical vapor deposition, electro deposition, or even by electrolysis deposition. There are many other techniques as well. The kinetics is basically dictated that all these chains come to the surface very quickly, but the time it requires is for organization. So, we can see it has a fast step of adsorption, thickness can be achieved in a few minutes, but it is the rate deciding step is nothing but the organization of these particular chains, because they take time in terms of corresponding in terms of basically acting towards the surface forces which are acting around. These are first of all the ionic or the forces with the substrate, and second thing is the weak or the secondary bonding with the nearby chains. So, that is what which requires very high time. Temperature, if we increase the temperature, it will try to basically form the coating or the layer at much rapid rate, but it will have many defects. So, if we deposit them at room temperature, it will improve the kinetics and reduce the defects. So, it will make it very crystalline. Concentration of adsorbate in the solution, if you have low concentration, it might require longer immersion time, but it will result high crystallinity. So, that is coherent with the lower temperature. Again, if the substrate is adsorbate is very pure, then the overall properties, physical properties of the SAM can be much better or much more predictable. So, that can also lead to the conformation of coating to a certain requirement. Dirt or contamination on the surface on the substrate can also cause certain defects. So, we can see the kinetics is basically being dictated by the rate in which the chains are getting organized, and there are certain temperature or pressure parameters. So, if you have higher temperature, it might lead to formation very rapidly, but then it will require it can create much more surface defects. So, lower temperature preparation can make it much more crystalline in nature. The kinetics basically will be comparable, though much lower, but it will have very lesser defects. And lower concentration can again impart higher crystallinity, because now they will have enough time. The overall deposition and then organization will be much more quicker than once the other entity is not. So, they can have enough time, because localization of these particular chains is much farther from each other. So, they tend to become much more crystalline, because they have now enough time available before a next entity is coming closer to them. Again, high purity is also very much required. So, we can predict what is the overall functionality that we can impart to the surface. And again, we can have selective assembly. We can make it either highly hydrophobic or hydrophilic in nature. So, we can have certain selective assembly. So, we can have organization of different parts. On a component. So, we can organize different zones in a particular component. So, it is again nothing but the extension of certain functionality. So, we can see that we can attain self assembly. So, if we start developing certain thiols and then start giving out functional chains of say maybe methyl, say on a gold substrate, if we can impart again thiols and then to make it hydrophobic in nature, and then again we can somehow try to impart an assembly, secondary level of assembly to this particular methyl group, and if we can polymerize a lubricant onto it. So, now what we can make now a layer which can take care of the friction, and if we and the remaining areas we can try to make it hydrophobic. So, we have assembly, self assembly of lubrication, and then this one will impart us hydrophobicity. So, in this case we are achieving lubrication. So, it will do nothing but it will reduce the friction of the moving parts, and this hydrophobicity will not allow no sticking of water droplets. So, we can achieve multiple functionality, or we can achieve a selective assembly of combining the various concepts of achieving more than one type of functionality to a particular component. So, a particular component has to be utilized in a wear condition where we have even water. So, we want to impart lubrication to it by polymerizing a particular polymeric chain or functional chain, and then we can also impart non-wetting to the surface by applying a layer. So, in that case we are able to achieve lower friction as well as super hydrophobicity or hydrophobicity on the same component. That is nothing but the selective assembly. By utilizing that we can achieve dual functionality. Then the assembly can also be stochastic in nature, which means it is difficult to predict. So, if you take a particular mica surface and then we put a water droplet and then we disperse some glass nanospheres. So, we have many glass spheres which are basically now which are there in a on a particular fluid on a water droplet. So, we have water droplet, we have a mica surface, and we are depositing certain nanospheres of glass. So, essentially once this particular water droplet starts evaporating, then we can see that then we can see that these microspheres of silica, they will start forming a structure on the mica surface. So, these are nothing but your glass spheres. This is water droplet and this is your mica surface. So, essentially what you will see a very nice organization of these particular particles of these spheres. If you zoom it up out here, it will look like this. So, we have very nice organization of all these spheres on this particular particle. It means that because of surface tension between the particles, because we are at some fluid layer or water layer on the glass surface or the glass spheres. So, as soon as the water is now evaporating, because of the capillarity action, all these nanospheres come in contact and they form certain organized layer. But this is very difficult to predict which type of how it will basically develop, because it has a similar probability in all the directions, but it will form a very nice dense organized layer that is called microassembly, and since it is difficult to predict, it is called stochastic microassembly. Again, there can be slight irregularities, can be basically they can come into picture, but that will arise because of the non-uniformity of the spherical particles or the spheres, because if there is some non-uniformity on the surface of the spheres, it will again lead to certain distortion. So, if one sphere has a bad surface, it might lead to a different orientation of the particles now. So, instead of coming like this, it might go something. So, if one particle is bad, say one of the particles is bad, it will basically destroy the entire microassembly. Again, application of SAMs, they can go from changing the surface properties of the electrodes. So, we can enhance the properties of the electrodes, we can enhance certain electronic properties, we can also utilize them in NEMS and MEMS, that is nano electromechanical systems or micro electronic mechanical systems, can be utilized for controlling the electron transfer. So, by changing the functionality of the surface chain, it can protect metals from harsh chemicals and etches like in thiols. It can reduce sticking of NEMS and MEMS in humid environments. It can alter the properties of glass. It can create either hydrophobic or hydrophilic monolayers. It can also be utilized for on the car windshields for keeping them clear of rain. So, these are the various applications of SAM. We can take them from chemistry to electronics to even hydrophobic entities or even biological units, where we can impart certain porosity or drug delivery using this particular monolayer. So, we can see that the overall application is not limited to any one entity, but it can go from myriad applications. So, in summary, we had Langmuir-Blodgett films, which are nothing but the lower interaction, the lower forces interaction, such as ionic or hydrogen bonds, van der Waals forces. Then we also saw that thiols have very high affinity for precious metals, so they tend to form a self assembly. Selenization, they have very high energy of the bonding, so they can be very toxic or explosives if it is so, but they can form very strong layers. But the only problem with them is if they undergo breakage of bond in any other direction, it can lead to a non-assembly or so. Then we also learned about the stochastic assembly. In this case, we can't predict how the assembly will occur, but again it is self-sustaining and can construct to a very regular structure. So, with this I will end my lecture. Thank you.